Here's a point. Functions describe reality around us. For instance, a lot of you make fun of me driving my little scooter to work. And rightfully so. I do look dorky. I do look nerdy. I look pretty pathetic. But here's the thing. I'm not sure if you're aware of this. A lot of you guys, especially the young men in here, are into sports cars. You mentioned a Corvette yesterday. If you buy a brand spanking new car from the dealer, the moment you drive it off the driveway of the dealer, the car's value depreciates. I want to say $5,000 just the moment you drive it off. So if I were to, watch this, if I were to graph, don't draw anything yet before I set you up. If I were to put dollar value of your car, brand spanking new, not a used car, but a brand spanking new car, the dollar value versus the time in years, okay, it would represent a certain kind of function, what we call an exponential decay. So let's say the car, you bought a Corvette. What's a Corvette now? Okay, let's just say, let's go in the middle, 50. Let's go 50 without automatic windows or something, okay? 59, what do I put in percent? So 50 grand, okay? Let's say a Corvette's 50 grand. The value of the car, as opposed to time, so this is 1 year, 2 year, 3 year, 4 and 5 and so on, the graph would look like this. The graph would not look like this. The graph would look like this. Radical decrease and then kind of tapering off as the years keep going. That's what it would look like. First few years, it's like dropping, skyrocket, because no one's going to buy a car that's 2 years old at the price of a brand new car. So it's going to dramatically decrease. But then as it gets older and older, it still decreases, but not as rapidly. You see. So these kinds of functions are called exponential functions. Exponential. And they look like what you see on your paper. Okay? We call them exponential growth, and if you flip your paper on the other side, just flip it really quick, you have exponential decay. So exponential growth versus exponential decay. Exponential decay is going down, and exponential growth is going up. Okay? These two types of functions model different things in reality. This is why we teach this to you. That's the whole point. Okay, so now, what does this function look like? Okay, the function looks like this. Go ahead and underline right here, or just put a box. The function will always look like that. F of x equals some number b to the x power. Notice how the x now, the input, is the exponent now, as opposed to what we've been doing in warm-up. The exponent is actually the variable, hence the word exponential functions. The input variable is the exponent. And they behave either this way, going up, or if you flip your page on the top, they behave going down, from left to right. I'm reading it from left to right. Going up or going down. So let's see. What are some of the features? In order for you to have a exponential growth, this number b, that number b has to be greater than 1. Okay? So any number greater than 1, 1.1, 1.2, 2, 10, 50. As long as that number is greater than 1, you're going to have an exponential growth function. It's going to look going up. It's going to look like that. Okay? What's up, Sylvia? Well, I'll show the plate here. So, now, what I want you to do here is I'm going to write example 1 underneath the notes, put example 1. And go to write the words graph. Let's graph. Let's just practice graphing these. Graph f of x equals 2 to the x power. F of x equals 2 to the x power. Okay. Put off, earphones off right now. All right. What would be my b value here? My b value. Anybody tell me what the b value is? 2. So the b value is 2. Tomorrow, when I throw a graph, an exponential function at you to graph it, for our sakes, we're going to make a table of values, and I want you to use the table of values that I'm going to give you. You can pick any x values you want. Remember when we make a table of values? I think Medina told us yesterday, you can pick any x values you want. You can. It just, for these kind of functions, it might make life very difficult for you. You start picking your favorite number and stuff. You can still do it. Don't get me wrong. But if you want life to be easy, use the values I'm going to choose right now for tomorrow's test especially, and for your assignments. And you're going to use these x values. Just for now, -2, -1, 0, 1, and 2. So right now, you're writing this on your note paper, but you're going to have your graph paper next to you, because we're going to graph this. But we're going to do the work right here on the note section. Okay? Let's do it. By the way, notice this is your input, and for our output, notice I didn't put y anymore because we're higher level. Y means f of x. We're using function notation now because we're higher Math 2 students. Math 1, I would have put y right here, but we're doing f of x. That means y. It means the same thing now. We know that. So let's do it. The first input value is -2. So let's do it. The function at -2 equals 2 to the -2 power. So right now, this is the note section at the bottom. We're gonna put the work on the note section, and we're gonna put the graph on the graph paper. So right now, let's just do the work here. I trust you guys did enough room, right? You guys have enough room there? The bottom. If not, just use the middle of the paper here. Since we're not doing the vocab, just use the middle of the paper right here to put this work here. Because we're not doing any vocab right now. It's just right here at the bottom. So let's see. Today's Thursday. I taught you how to do this on Monday. How do I handle 2 to the -2 power? It's a fraction, huh? Remember the negative exponent rule? This becomes the reciprocal with the positive exponent. Notice that. I reciprocated with the positive exponent. So the function then at -2 becomes 1/4, huh? 1/4. So let me put that right over here. 1/4. Question so far? So today's lesson on graphing exponential functions involves what we learned on Monday. This is the way math is. There's a progressive element to it. Things build upon each other. We couldn't do this function if we didn't do that first lesson on Monday. There's no way. You would have had nightmares. Next one. The function now at -1 is going to be 2 to the -1 power. Negative exponent rule. This is all over 1, so we just reciprocate. It's going to be 1 over 2 to the first power, which is just 1/2. We're rocking and rolling. The next input, a function at 0. That's going to be 2 to the 0 power. What's anything to the 0 power?
1. 0. 1. 1.
0 power exponent rule.
Oh, the exponent, it wouldn't be itself. Exponent.
But if it was 0, it becomes 1. That was day 1. That was on Monday. I tell you the 0 exponent rule. Everything to the 0 power becomes 1 except there's only one number in the universe that if you take it to 0 power, it doesn't become 1. What number was that? Nice. Medina's on this. Good guess. So 0 is the only number. In other words, you can't take 0 to 0 power. That number doesn't exist. But every other number, if you take it to 0 power, became 1. That's what we learned on Monday of summer school. That's the first lesson of summer school. I'm sorry. That was my fault, wasn't it? So, input is 0. Output is 1. We're rocking and rolling. We're rocking and rolling, you guys. Who likes rock and roll? Me too. Who can play rock and roll? What instrument? Nice. Electric or acoustic? Last day of school, I'm going to bring the equipment. We're going to jam. Chim and Mungia are going to jam. Here we go. Next input. The function at 1 is equal to 2 to the, I'm replacing x now with 1, to the first power. What is 2 to the first power? It's 2. We're rocking and rolling. You guys with me? Again, life will be very simple if you use my table of values, the -2 to the +2, life will be very simple. You can start using any x value you want, but just, you might go off into some other land and become scared, but it'll work. Last one, last input is f of 2. The function at 2 is 2 to the second power. That's 4, huh? So the function at 2 is 4. Right, Jim? Okay. We got, let's see, 1, 2, 3, 4, 5 points to graph. You have the graph paper I just gave you. On your graph paper with me, let's go to make a tape. Let's make a x and y axis. Me a y axis. X axis. I hear a lot of talking right now. Right now I have the floor, so we need some silence. Let's get our papers out. Record. X and Y axis. We're good? Need a pencil or what?
I was just gonna wait.
I got you. You need one. Got you. All right. I got the first point here. Let's see here. The first point is, what do we got here?
-2.
1/4, nothing. Nice. There we go. So -2 1/4 would be a fourth of the way up. Here's 1/4, 2/4, 3/4, 4/4. So -2 and 1/4 would be right here. A little bit above the x-axis.
-1 is half.
You're the man. -1, half, right here. A little higher. 0, 1. 1, 2. 2, 4. Now, if we kept going towards the negative x-axis, if we kept picking x values to the negative x-axis, this graph would get closer and closer to the x-axis but never touch it. So I'm going to put an arrow here. It gets a smaller and smaller fraction, getting closer and closer to the x-axis but never touching it. And then it comes over here and it starts curving up, and it goes to positive infinity this way. There's an exponential growth function. Now, right here, as it gets closer and closer to the x-axis, there's a special word for that. It's on your note guide. It's got a funny sounding word. It's called an asymptote. An asymptote. Very mysterious. That graph gets closer and closer to the x-axis without ever touching it. It gets infinitely closer without ever touching it. Because a fraction gets smaller and smaller and smaller, ever so infinitely. So the asymptote would be the x-axis. That graph gets closer and closer, but with never touching it. So when you draw that curve, you got to know, even though it looks like this graph is touching the x-axis, it actually never touches the x-axis. That word is called the asymptote. It's kind of like if I think how mysterious this would be mathematically. The distance between me and Moreno, let's say I got closer to Moreno. Every step I take will be half of the distance I was prior. So from me to Moreno, it's probably about 10 feet. If I get halfway there, be right here. And now I'm gonna get closer halfway from my previous position. Be about right here. Imagine me doing that infinitely, getting closer and closer to Moreno, but just halfway from the position I was previously. I would actually never reach him. Theoretically, I would never actually touch him. I'd get closer and closer to him, but only halfway from the position I was previously. How long can I sustain that? How infinitely can you divide a fraction in half? How many times can you do that while your mind can go on infinitely? That's kind of what's going on right here. This graph is getting ever and ever so closer to the x-axis, but never actually touching it. We call the x-axis, put this on your notes, put right asymptote. It's got a weird sounding name, asymptote. We're going to last, Medina. So here we go. This morning, right when we got to school this morning, we dealt with an exponential growth. Okay? This kind of function will model like the bacteria growth in a petri dish or in any type of biological system. Bacteria grows exponentially. If you leave some food out, not refrigerated, the bacteria growth models an exponential function. The population would be your y, and time would be your x. That's exponential growth. Now let's talk about exponential decay. Decay means it's going down. Like I said this morning, if you buy a brand spanking new car, it'll model an exponential decay model, an exponential decay function. So we got to know how to graph these. Okay? Same type of deal. Underneath right here where it says notes, Let's go ahead and graph. Let's graph g of x equals 1/3 to the x power. Let me put a parentheses around the 1/3 because it's the whole fraction being raised to the x power. So 1/3 to the x power. So that's how you know that we're dealing with a decay function, because the value of b, remember bx, b to the x power? The value of b, notice, look at the way they describe it. It's greater than 0 but less than 1. Well, that means it's a fraction. If you have a fraction for the b value and you have the exponent, it's going to be a decay function as opposed to a growth. Let's graph this puppy. But let me rewind again. So I want you to absorb that in your mind. We're going fast in summer school. You got to absorb this. If the b value is a fraction, look at greater than 0, less than 1. If it's a fraction, it's going to be a decay. Okay? Remember that for tomorrow's test? If it's not a fraction, like what we had right here on this morning, the b value was 2. That's not a fraction. It's a whole number. Even though you could write it as a fraction. You get what I'm saying? If it's a whole number, you're dealing with growth. It's rock and roll. Remember, to make life easy for yourself, the table of values you're going to pick is the one I'm prescribing. The table of values starts at -2, -1, 0, 1, and 2. This will make life easy for yourself on tomorrow's exam. But g of x, watch this. By the way, assignment 7 is on a piece of paper. You're going to have to graph some of these on your own, on graph paper. Just a little FYI for those of you already ahead on 7. G of x equals the first input value is -2. Let's do this. So I got 1/3 to the -2 power. That looks funky, weird, scary, and frightening. But have no fear, because on day 1, we went over the rules of exponents. Right? G of x, then watch this. My bad, it shouldn't be g of x. I have the input value. What's the matter with me? My coffee hasn't kicked in again. Dang it. I'm going to tell my wife to give me better quality coffee or something. I don't know what's going on here. So it's g at -2. Yeah, so like, yeah, what do we do here? Good try. There's an exponent rule I can apply here. We'll flip it after we take every item in parentheses to the -2 power. I think that was the 7th rule. It was called the quotient of powers. Quotient of something like that. Power of a quotient, I think it's called. The 7th rule. Watch this now. I'll take the 1 to the -2 power. Nice. I'll take the 3 to the -2 power. Nice. We're rocking and rolling. Now we'll use a negative exponent rule. So g at -2 is going to be, watch this, whatever has a negative exponent moves. So this goes to the bottom with a +2 exponent. This will go to the top with a +2 exponent. Remember, we reciprocate. We flip that puppy. So g at -2 then becomes what? Thanks, guys. Appreciate it.
What?
1 over 1? Right, 9 over 1. 3 to the second power is 9, so 9 over 1 just becomes 9. There's our first point that we're going to plot. -2, 9. A lot of work? That's crazy, huh? Shame on me for making you work and think, at school especially. Let's go on the second input. I'll stay with green. The function at -1 equals 1/3 to the -1 power. Again, this is on the notes section of your note, the handout. Keep the graph paper for the graph right now. Put all the work on the notes section here. Okay, let's do it. G at -1. The 7th rule says every item in parentheses, take it to the outside power. So I'm going to take 1 to the -1 power, 3 to the -1 power. Yeah? So G at -1, reciprocate, that becomes 3 to the positive 1 over 1. That's 3. We're rocking and rolling. Right, this goes to the bottom. Question so far? Zero is always easy. Because anything to 0 power is what? It's always 1, huh? Everything to 0 power is 1. So look at your note guide real quick. Look at the growth function. Look at it. It's always 0, 1. It's right there. That's like an automatic, in other words. Or look at the decay. 0, 1. That's like an automatic point because we already know anything to 0 power is going to be 1. So you can put that point without even thinking about it. So, where am I? Oh, yeah. So 1/3 to the 0 power is going to be 1. I'm not going to do the work. I'm not even going to do it. Next one's the input of 1. G at 1 equals 1/3 to the 1 power. G at 1, 1 to the 1 power is 1, 3 to the 1 power is 3, 1/3. So this will be a 1/3. So you can start seeing we're getting closer and closer to the asymptote. It's going to get closer and closer to the x-axis, ever so closer. It's coming down like a roller coaster. From 9 to 3 to 1 to 1/3 is starting to level out. Watch. How about you? Speaking of roller coasters, I haven't gone to Magic Mountain in a long time. I'm due for a visit. I love Magic Mountain. Summertime, I gotta go visit Magic Mountain. 1/3 to the 2nd power. G at 2 is 1 to the 2nd over 3 to the 2nd. We're rocking and rolling. So G at 2, 1 times 1 is 1. 3 times 3 is 9, 1/9. Okay. Graph these puppies. You have your graph paper from this morning? Did you say that?
That was me.
Oh. Who says? Okay, so go ahead and give me a. I'm gonna go Dodger Blue since they're gonna win tonight, right, Donis?
We won yesterday.
Nice. So give me an x-axis. We'll go from, let's see, 1 to 9. And give me a, actually give me a, that was a y-axis. Here's your x-axis. Specifically, this is actually the g of x axis because we don't deal with y anymore. Remember, y is always g of x or f of x. Here's your x-axis. We went from -2, 1, 0, 1, and 2, right? Let's do it. But Dina, what's the first point? Negative 2 what? The first.
Can I write it down?
A big move. Negative 2, 9. Negative 2, 9's right here. Joshua thought it was the second point. Negative 1 what? Negative 1, 3 is right here. Remember the automatic point is 0, 1. Look at 0, 1. Some of you are not writing stuff down and you're giving me an ulcer and stressing me out. The next point was 1, 1/3. Look at 1/3 would be 1, 2, a third away up. Right there. And then 2, 1/9. That'd be like a ninth of the way up. That's like real small. Let me get the little finer pen here. 1, 2, 3, 4, 5, 6, 7, 8, 9. A ninth of the way up. Look at it be like right there. Of course, you're just estimating, obviously. It's closer to the x-axis, but not touching it. Let's draw our curve. Let's draw our curve. Coming down. Curve in like a half pipe for your skaters out there. Closer and closer to the x-axis, but without ever touching it. I'm going to put an arrow up here because that goes to positive infinity. What's the x-axis called in this case? It never touches the graph with asymptote. 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 Those of you going to university and getting higher mathematics, you'll see a lot of asymptotes when you get to other functions. Say again. That's it, huh? You're done? You hanging up the cleats?